Hi everyone, and welcome to a workshop on building a simple neural network image classifier with Keras. Our goal in this workshop is to build a simple neural network image classifier that classifies handwritten digits based on their respective number. We're going to be testing it on the test set and eventually on hand-drawn images of our own. This is meant to be a beginner-friendly tutorial, so we won't be going into too much of the details and the math behind our neural networks. I'll just be showing you how to get everything working. But I would definitely recommend looking into the theory behind it if you are interested. In this workshop, we're going to be obviously using Keras, which is a simple and abstract high-level deep learning API. The Keras API is very easy to use and to build models with very few lines of code. Keras is also built on top of TensorFlow, which is an open source library for deep learning. Because of its popularity, Keras is actually now the official API of TensorFlow, which means that installing TensorFlow gives us access to Keras by default. Because we're going to be working with a lot of matrices, we're going to be using NumPy. And obviously, Python is our language of choice. For our dataset, we're going to be using the MNIST dataset, which is a standard dataset for handwritten digits. So here's a general overview of what exactly we're building. For our intents and purposes, a neural network is essentially just a complex network of equations. We want our neural network, or model, to accurately predict the digit based on the image we give it. To do this, we need to train our model. The goal in training our model is to minimize a loss value, or the error between a predicted value and the actual value. This will be given by a loss function. So let's say we feed in our model some input data. When we predict the wrong value, we want the loss to be very high, and conversely, when we predict the right value, we want the loss to be very low, or 0. This is so that when we minimize the loss, we in turn make our predictions more accurate. Obviously there's a lot more to this, but we're keeping it simple here. As a whole, a very simplified explanation of the training process looks like this. So first, we feed in some input data, in this case our image data. Our model makes a prediction and we calculate the loss. This is also called feed forward. Next, our model will self-correct in a process called backpropagation. We repeat this until we see that our loss has converged to some value. This stuff is all really done behind the scenes when we train our model, so there's no need to worry about if this stuff doesn't really make any sense. We will also see that Keras provides some metrics to help us see what is going on when we're training. So here's a roadmap of the steps we'll be taking. First is the data preprocessing stage. Second, we'll be constructing our model. Third, we're training it. And fourth, we'll be testing it. Thankfully for us, Keras makes each of these steps very user-friendly. So let's get started. Alright, let's get started. So if you haven't done so already, navigate to your working directory. Next, we need to install some dependencies. Because we're using Python, I'm going to be using the pip3 install command, and the packages we're going to be needing are NumPy, TensorFlow, as well as the MNIST dataset. So as you can see, I already have these installed, but for you this might take a bit longer. Alright, next let's open PyCharm, or any IDE of choice, and let's open that project. Alright, now open a new file, and let's call this image classifier. Alright, cool. So let's start with some import statements. So we're going to be needing NumPy, so let's import NumPy as MP, and import OS as well, and import MNIST. Oops. And next, from TensorFlow, .keras.models, we're going to need something called sequential, which is just a type of model. Next, we're going to need, from TensorFlow, .keras.layers, we're going to import dense, which is, as you can tell, a type of layer. And then finally, we're going to import from TensorFlow .keras.utils, we're going to import a function called toCategorical. And this will be used in data preprocessing, as you'll see later. So now we'll be on the data preprocessing step. All right, data preprocessing. If you recall back to when I mentioned that a neural network is sort of like a complex network of mathematical equations, in that case, well, we're going to need to be able to represent our images in a way that is compatible with these equations. If you think about what images really are, they're just a collection of pixels, with each pixel having a certain color value given by a mixture of 3 colors, red, green, and blue. Each color for the pixel has a number describing the intensity of that color, ranging from 0 to 255. In this case, however, our images are going to be black and white, so instead of RGB values, they will instead have a singular value from 0 to 255 depending on how black or white it is. So here is our workflow. We take our image and then we convert it into a matrix of pixels so that our machine can understand it. Then we normalize these values and then flatten it to a vector of pixels. These last 2 steps, we'll see exactly what they mean when we start coding it. But also, the MNIST dataset gives us our image already as a matrix of pixels, so we don't have to do that step at all. So let's see what this looks like in code. All right, let's get to coding the data preprocessing step. So first, let's get our training data. So let's call the set of images train images, and we're going to get that from MNIST by calling a function from the MNIST API called train images. And remember, this is going to return a matrix of pixels representing each image, or should I say pixel values. Remember, it's going to be a number from 0 to 255 that represents its quality of how black and white it is. And for each image, we know that we need a label as well. So let's name this train labels, and this is going to be whether or not it's 0 or 1 or 2, for example. And let's get that from MNIST as well, called train labels. And these 2 data sets should be in order. So, the first image will correspond to the first label, etc. And next, we're going to get a test set. So it's really important that our test set is different from the training set, so we know that our model is generalizable. So let's just grab that and let's call it test images. And we're going to do this the exact same way as we did before. So MNIST.test images and test labels equals MNIST.test labels. Awesome. Okay, so next up is mean normalization. So what mean normalization basically does is it centralizes the values within a small range, usually or typically from -1 to 1. And what this does is it speeds up the training process by a lot, because operating on smaller centralized values is typically faster than working with bigger numbers. So right now our pixel values range from 0 to 255. So what we can do is we can modify that. So let's take our train images matrix, and we can modify it. Let's first divide it by its own range. So we know that our pixel values range from 0 to 255. So what this does right now is it takes every value and makes its range from 0 to 1, since we're dividing by the range, right? And let's centralize the mean to be 0. So we subtract 0.5. Now our range is instead not from 0 to 1 now, but from -0.5 to +0.5. And we can also do the same thing for the test set. So test images equals test images over 255. And let's subtract 0.5 to set its mean to be 0. Okay? And that is mean normalization. All right, so the next step is we need to flatten our vectors. So right now, MNIST gives our images as 2D vectors or 2D matrices, and each matrix is dimensions of 28 by 28. So we want to be able to pass in each input to our model as a one-dimensional matrix. So what we can do is we can actually use the numpy function called reshape and do this for us. So this is going to be flattening our inputs to 1D vectors. And let's modify train images. So we're going to set that equal to train images.reshape. And we're going to pass in -1 as our first parameter, which means that we're basically telling NumPy to figure out the first dimension. And because we're working with 28 by 28 images, if we extend it into a single vector, you can multiply 28 by 28 to get the number of pixels, and we're going to get a pixel vector of length 784. And let's do that same thing with the test set. So test images and then test images. All right, so we're done with the data preprocessing step now. All right, so on to the next stage, which is constructing the model. So this is honestly pretty simple with Keras. There's not much work to do. It's honestly just a few function calls. But we do, however, need to specify the model type, the layers, as well as the activation function. These three things are outside of the scope of this workshop, and they're honestly pretty complex in the way we choose them. However, if you do follow the directions I've given you, everything should work out, and you don't have to understand exactly what's going on. All right, so let's get to coding. Okay, so let's first create a new model variable, and let's set that equal to the sequential model that we created from or imported from before. And we're going to pass in some layers. So again, just follow along here. Don't exactly have to understand what's going on, as long as you just follow along. And this will be our last layer. Softmax. Okay. So next, we're going to compile our model and give it the correct settings. So we can just do model and then run the compile function. So we're going to give it some parameters. Our first one is going to be an optimizer. So basically the Atom optimizer is just going to help speed up and optimize training. And next we're going to give it the right loss function, which is categorical cross entropy, which is a loss function that's really helpful when you're dealing with classification problems like we are, and metrics, which is just going to help us display some data when we're training. And we're going to give it accuracy. All right, and I think that's it. Our third step is going to be training the model. Again, there's not much work to do. However, we do need to specify the training data set as well as their respective labels. We also want to specify the number of epochs, which is the amount of times the model sees the entire data set. You can kind of think of this as like a run-through of sorts. After each run-through, our loss will usually decrease until it converges to a certain value. We also want to specify the batch size, or the amount of samples each model sees, or the model sees before it self-corrects. We also want to save the model after training. So if we do happen to pause or stop training in the middle of our session, we can pick up from where we left off before if we just open the script again, and then load in the models and start from there. Okay, so let's start running the training part of our model. So training the model is actually just as simple as calling model.fit. So in this function, we're going to pass in a few parameters. Our first parameter is going to be our training data set. In this case, we're using train images to represent our images. Next, we want to pass in our labels. So if we pass in train labels as is right now, For each image in trained images, that corresponds to a single-digit representation of what that image is. For example, if one of our images here is a 9, that's going to correspond to the number 9 in trained labels. However, Keras expects, in this case, a 10-dimensional vector as its classification label. This is because we have 10 different outputs, or 10 different possible outputs for each digit from 0 to 9. And to fix this, we actually are going to use this function that we imported before called toCategorical. So what toCategorical does is it one-hot encodes a number. For example, if we pass in the number 2, we want this to be represented as a one-hot encoded vector, which means that for each index, or for each index that's not 2, we're going to get 0 for that array, or for that vector. But for the index that is 2, it's going to be 1. And this is again a 10-dimensional vector. So this is an example of what one-hot encoding looks like. And this way, Keras can know that the output is 2 instead of having just single-digit representation. So let's call toCategorical on train labels. Okay, cool. Next, we're going to specify the number of epochs. In this case, we're only going to use 10 because our model isn't really too complex and our dataset isn't also that complex either. But usually you would use more if you're training a more complex model and your dataset is much larger. And we're going to use a batch size of 32, which is a pretty standard batch size. All right. So after each, model train or model fit session, we should save the weights, right? So we're going to do model.saveWeights to save the weights. And let's call this file path image classifier dot h5, which is going to be the extension. And comment that with a save model weights. And if we want to resume training, we should, before training the model, we should load in those weights so we can resume from where we started before. So before model.fit, let's actually do something really quick that checks if we have already a model saved. So let's do if os.path.isFile, and let's give it the path name that we have before. And if that's true, then we want to model.loadWeights. And let's also give that the same file name. All right, and this is going to be load the model from disk if there exists previous weights. All right, so far that's looking good for training. So our last and final step is going to be testing the model. We're going to be evaluating the model accuracy based on the test set. However, we can also use the predict function to see what the model outputs and then manually compare and examine each predicted output. We're going to be using both these methods, as you'll see in the following code. Okay, let's get started on our final step. So we're going to be evaluating the model, and again, this is actually really simple. So all we need to do is do model.evaluate, and then we're going to evaluate that on, again, our test images and also our test labels, but we first need to one-hot encode them. So test labels, and that should be it. So this will just output some metrics once we call that function to the standard output, and we'll be able to see how well our model performed. So next, our manual method is going to be pretty similar. So let's make a new variable called predictions. And we're going to set that equal to model.predict. Instead of evaluate, this is just going to give us the straight up output of our model. And let's actually just call this on maybe the first 10 images and test images. So we're going to predict on the first 10 images. And next, we're going to print out the actual digits that the numbers are for the first 10. So let's print out actual digits. And the actual digits will come from test labels. So let's just print out test labels. And again, let's get the first 10 of them. And now we just add a comment here. So print actual 10 or first 10 digits. And from test set. And then let's print out now our model's predictions. Okay, so in order to do that, we first need to do some work on predictions. So right now, predictions is going to output a vector similar to this one hot encoded vector, but instead each index will have a certain probability as their element. For example, if index 0 has a value of 0.5, that means that the number or the number 0, because it's at the 0th index, has a 0.5 probability of being the correct classification. However, what we want to do is we want to grab the index that has the highest probability, which means that it is the most likely to be classified the number at that specific index. So for example, if index 10 over here, corresponding to number 9, has a value of 0.99, we obviously want to choose that one because it seems like it's the most likely to be the correct classification. So what we can do is we can use a NumPy function called argmax, which is going to do exactly that. It's going to return the index of the highest value within that vector. So let's call argmax on predictions, and because we're going to have predictions as a row vector, we're going to maximize along axis 1, which is going to be the row dimension. And that should be it. So let's actually go ahead and train the model real quick and run this function, and we'll see the output. Just give it a second to load. Yeah, sometimes this happens. It's not too big of a deal. It should work just fine. So as you can see, we're getting pretty good results so far. We have around a 97% accuracy, and you can see that the first 10 digits, we all classified them correctly. So that's it. So that's it. Thank you so much for watching. In this part of the workshop, you learned how to pre-process image data to train a model, you'll learn the steps needed to construct, build, and test a model using Keras, as well as how a neural network generally works. So stay tuned for the next part of the workshop, where we will learn how to make our own test set with our own handwritten digits. And again, thank you so much for watching, and I really hope you enjoyed.